We're going live in the Beehive. Fun stream coming up. Let's see if we can hear this. Beautiful. Looks like we can. Okay, friends. I'm going to pop out the Twitch chat. We're streaming this live on Twitch, by the way, so if you're watching this in a future date, all of this coding, example, and whatnot was done live. So we're going to be working on, this is my PyTorch course. If you've already been through it, you may be familiar with what's happening here, but you can get all the materials that you need on GitHub. And if you're joining in the chat, if you're watching this live, please let me know how the audio and the video is, just in case something messes up. Now, I'm going to do the exercises for Module 6. So if we go to the Extras tab, there's Exercises and Solutions. So for the past couple of sections recently, I've been making live coding exercises and solution walkthrough. That way you can kind of see how I work through problems, how I solve them, how I run into errors, and how I troubleshoot different things. So there's the other notebooks there from 02 to 05. We are now up to 06, PyTorch Transfer Learning exercise solutions. So the idea of these would be that you would complete these exercises. Well, I'm going to do the solutions in this stream, but you would complete these after going through Module 6, and that is PyTorch Transfer Learning. So there's what is transfer learning. So the whole point of transfer learning is to allow us to take the patterns, also called weights, from another model and use them for our own problem. This is a very, very powerful technique in deep learning. It just means that we can take something that's already working and apply it to something that we would like to use it for. For example, if we take a computer vision that's been trained on, a computer vision model that's been trained on ImageNet, we take a network such as EfficientNet, which is a great model, and then we put that into our own problems, such as classifying images of steak, sushi, or pizza. Nice and simple image classification problem. We can generally get pretty good results straight away. French Toast Mafia, what's going on, my friend? Good to see you. There are a fair few places to find pre-trained models on the internet. One of the main ones is the PyTorch domain libraries, such as Torch Vision and Torch Text. They all have a models section where you can find pre-trained models. Then also we have the Hugging Face Hub, which is a great place for finding machine learning models on almost any topic you could imagine. And then there's, of course, there's another specialized library such as TIM, which is PyTorch Image Models Library. And then you have Papers with Code, which collects all of the latest state-of-the-art machine learning research, but it also has code repositories for these. So if you find something here that works pretty well for your type of problem, for example, you can go up here, state-of-the-art for image classification. You can generally find the code for the best performing models here. So such as Coca that just came out, CFAR 10, yada, yada, yada. We've got a whole bunch of different benchmarks here. So let's just get out of this. This stream is focused on doing the exercises for PyTorch Transfer Learning. All the materials here are at learnpytorch.io. So that's, you would have already have gone through this, learnpytorch.io, section 6, before we complete these exercises, but I'm just going to do them from scratch so that you can see what it's like. So we go through this, we get the data, we create data sets and data loaders, we create a transform, we get a pre-trained model, we train the model, we evaluate the model, and we make predictions on an image from the test set and also on a custom image. So that's really fun. That's where machine learning really shines, is when you're using it on your own custom data set. So there's a summary of what we would have covered. Now we're doing the exercises. So this is the exercise template notebook. That won't be linked just yet. So I'm going to open up this PyTorch Deep Learning Extras Solutions. This is the notebook I'm working on in this stream. Ravi from California, how you doing? Welcome to the stream, my friend. So I'm just going to copy this to my drive. So this is from GitHub. Again, PyTorch Deep Learning, Extras Solutions. I'm working on this one. We're going to work on the code solutions here. I'm just going to get out of all this. I think I only need this right now. Oh, did I just get out of the wrong tab? Excuse me. But yeah, the exercises are here. So number 1, make predictions on the entire test data set and plot a confusion matrix for the results of our model compared to the truth labels. Okay, let's see how we can do that. Just going to save this. I'm going to make sure I have a GPU. Make predictions on the entire test data set and plot a confusion matrix for the results of our model compared to the ground truth labels. Okay, so we're kind of gonna, this is a tough one actually to run in this notebook. So what we're going to have to do is we're going to have to get the code from the previous notebook to have that trained model. So again, we're solving these live on stream. So I'm going to go into notebook number 6. I might put a note here. Note, you will need to get the trained model / retrain the model from notebook 06 to perform predictions. You'll need to get the trained model, or you need to get the data set as well. So this is good to know. So we need to get the model. We could do this from the book actually. That might be easier. Because conveniently, the book version of the course has this little copy button that we can do. So import required libraries /code. Then I'm going to set up device agnostic code. I'll just make sure I have a GPU. And then I'm going to get the data. Set up the training directories. And create a transform here. So this is just rerunning the code from the Transfer Learning notebook. Oh, do I not set training directory? I'll just make a few code cells here. Can we see what's going on? So all we're doing is we're preparing a model here. So I'm going to use EfficientNet B0, pre-trained. And then I'm going to make sure that we've unfrozen some of the base layers. Or sorry, freeze the base layers. Then I'll change the classification head so that it's set for our data set. So our data set, just recall, is images of pizza, steak, and sushi. So pizza, steak, sushi, training and test data set. That's what we're doing. We're building an image classification model using transfer learning to classify images of pizza, steak, and sushi. So we're going to train the model here. Boom. And then we should have a pre-trained model by then. Wonderful. This shouldn't take too long to train. Make predictions. So this is all we've done so far. We've just got some code. For exercise 1, here's what we're doing, making predictions on the entire test data set. We've got all the code from the previous notebook, so from section 6, to give us a trained model. So now we have a trained model, which is an efficient net B0. That's all we've done. We've just taken the same code from here and put it into a few cells. So now we need a way to make predictions on the entire test data set and plot a confusion matrix for the results of our model compared to the truth labels. Okay, let's see how we can do this. So test data loader. I think we can go make predictions on the entire test data set. We want a list. So test preds. I might zoom in here so you can see what's going on. I'll put this over here. I like this on the left. You built a deep learning computer. A 3070 Ti, nice. How's that going? How much memory does a 3070 Ti have? So we want a list here. We actually don't need this anymore because we're going to be writing code. So test preds. So let's put the model into evaluation mode. And then with torch.inference mode for predictions, we want to for x, y in, I wonder if we have TQDM. We'll get TQDM in TQDM test data loader. Let's send it to the device. So what do we have to keep in mind for predictions? We have to make sure the data is in the same shape as our model, and it will be because we're using the test data loader. We have to make sure the data is in the correct data type. And then we just want to pass the data through the model. So test logits, because the raw output of a model is logits. Model X, convert the pred logits to pred probs equals, we can do that with torch.softmax on the test logits, and this is going to be across the first dimension. Then we'll convert the pred probs into pred labels. So pred labels equals torch dot. I don't think we need a list actually. Let's see what this does. Torch.argmax. Oh, I think we do actually, because this is going to loop through each batch. So, because it's loop through the batches in the test data loader. So right now our test data loader is batches of images. So length of test data loader. It won't be very many. Yeah, we've only got 3 batches, but that's okay. So let's add the pred labels to test preds list. So test preds dot append pred labels. Then let's have a look at test preds. This shouldn't take too long. There we go. Okay, beautiful. So we need a way to concatenate this. I think if we just go torch.cat, Oh, what did we get wrong here? Beautiful. Okay, so we've got the test predictions. And now we need make a confusion matrix. Test truth equals test data loader. Can you get targets from this? What do you get from this? Can you get, I want to see if you can get the labels. We might just have to iterate through. I'll just get y for xy. Yeah. Get the truth labels. Test data set for xy in test data loader. Okay, beautiful. So we've got the truth labels and we've got the prediction labels, and we want, now if we go to learn PyTorch.io, there's actually a way in here to make a confusion matrix. So this is what it's about, not knowing, you don't necessarily know all of the code that you need off by heart to begin with. Yeah, so that's similar to what we did. But now we need, I'm going to import torch metrics and ML extend to make a confusion matrix. So I'm going to import these. We just need to make sure ML extend need the following libraries to make a confusion matrix. Torch metrics, ML extend. So torch metrics is a great package for getting a bunch of different metrics in PyTorch, PyTorch style. And ML extend is by Sebastian Rashka, which is, he's a amazing machine learning teacher slash, yeah, here we go, machine learning and AI researcher. And he's got a fantastic library with a bunch of useful machine learning functions that don't really exist anywhere else. So we're going to import both of those. So this is just some code to see if we can import torch metrics or ML extend, and if we can't, we're going to import them. And we've got some checks here to verify that ML extend should be version 19 or higher, because that's where the functionality that comes in that we want. So this is what we want to create. So let's just write this out by hand for a little bit of practice. So from torch metrics, import confusion matrix, and then from ml extend dot plotting, import plot confusion matrix. And this is going to just show us where our model is getting confused. Set up confusion matrix instance. So confmat equals confusion matrix. We'll pass in the number of classes. Do we have a class names variable here? I'm not sure. Right now, our class names should be, yeah, pizza, steak, and sushi. So the number of classes that we're dealing with is length class names. So that'll be 3. I think that's all we need to instantiate our confusion matrix. And then we create a conf matrix tensor. We'll do that with confmat preds equals y pred tensor. And then target, or actually it doesn't, I'm copying too much here. So we need test preds, which is just what we created up here. Test preds, and we want to compare that to the test truth. So preds equals test preds, and the targets equals test truth. And right now, this should look like a tensor, I believe. But we want to plot it. We want it to look visual. Oh, I might need this on the target device, maybe. Here we go. Oh, target. Yeah, there we go. Okay, beautiful. But we want to plot this. Plot the confusion matrix. So this is again from Learn PyTorch.io. Plot confusion matrix, very helpful for classification problems. So fig ax equals, this is from the ML extend library, plot confusion matrix. We want confmat equals confmat underscore tensor. We want to make sure it's in numpy because this is going to leverage matplotlib. Matplotlib likes working with numpy. And then class names equals class names. So our variable with just a list of the different classes that we're working with. Because remember, what we're building in this notebook is a computer vision model to classify images of pizza, steak, and sushi. So let's see our confusion matrix. Here we go. Beautiful. So we know that our model is performing quite well based on the test accuracy up here. 90% correct. So it does get a few instances wrong where it's predicting... Wow. Okay. So it predicts... It's predicting sushi 3 times when it should have been pizza. And it's predicting steak 3 times when it should have been sushi. And it's predicting steak as well twice when it should have been pizza. But it looks like it gets sushi pretty well correct all of the time. True label, predicted label. So that's pretty darn good. So what we can do now is get the most wrong of the predictions on the test data set and plot the 5 most wrong images. So this is a fun way to sort of troubleshoot your classifiers, or just troubleshoot your machine learning models to see which instances are the most wrong, which means where did our computer vision model, where did it predict the wrong class, but with a very high prediction probability? So what we're going to do is we're going to invert, we're going to do predictions across the whole test data set, and then we're going to sort by wrong predictions, so we know which ones it got wrong, and we're also going to then sort by prediction probability. So then we want to find the samples, the 5 samples that have the highest prediction probability, but were wrong. I really like to do this. So we're going to need a few things. Let's create a data frame, and we'll sort these with sample, or maybe with, yeah, I think we should get the image path. We want a data frame with sample, then we want label, then we want prediction, and then we want pred-prob. So this will be a good data frame. So we want all the paths. We could probably create a list of dictionaries to do this. I think that'd be the best way to do it. Yeah, okay. So first of all, get all. Can we get from our test data loader? I don't think we can get the file paths. That's okay. Why don't we just code this from scratch? Yeah. So get all test data paths. So here's what we're going to do. We'll code this from scratch. Import, we want to, it'll make more sense when I code it out, but we want to get a list of all the path names, so that way we can track the samples. And we want to extract from that the labels, so we can create a dictionary with all of this. I want to get a list of all the samples. That'll be all the file paths from the test data set. List of all those, all these paths. And then we can, from that, we can get their labels, so the ground truth. So we will know the ground truth labels. And then we want to make a function that predicts and calculates the prediction probability. So we could probably do this all in one hit. And then we want to return a list of dictionaries. A list of dictionaries with one of these dictionaries per sample. So let's do that. Import test data paths equals list. We want path tester, because recall that our tester is that, but then we want it to fit the glob of star.jpg. Beautiful. All those paths. There we go. Now we can get test labels equals, we can iterate through this. We want, these are the labels for each image, right? So the test labels equals path dot, I think it's parent dot stem for path in test data paths, test labels. There we go. Okay, there's the labels. Beautiful. We've got a way to get the labels. So let's create a function now. Create a function to return Hey, Master Wayne, what's going on? Any dates, prior dates for releasing this course on Udemy? I'm not sure. The videos are currently being edited right now. So I'm looking, what's today? About a month from now, maybe, to release the course. I don't know the exact date it will be on Udemy, but it'll be very soon. I've got all the materials done for, I'm going to shoot the videos for this section 06 soon, but we're going to create a function to return a list of dictionaries with sample, label, prediction, pred-prob. So def, pred, So this is going to take in, and then we want to loop through, and then take in our model as well. So for path in so we'll make a pred dictionary, and then so we want to get class name, so predict equals path.parent.stem, and then we want to get sample path. A list of dictionaries is one of my favorite data structures. So image path equals path. We're going to create empty dict to store info for each sample. And then we want to predict, get prediction. So this is where we have to open the image. I'm going to, what should I open it with? Maybe Torch Vision IO. No, I need to use, because I need to transform it. Get prediction. From pill import image. Image equals image.open path. And then I want to image equals transform on the image. And then I want to model.eval, and then I need to expand the dims here. Unsqueeze. Open image. Transform image and add batch dimension. So I actually don't need torch vision there, model.eval. We'll just do this all from scratch, hey? With torch.inference mode, let's do a prediction. Predlogit equals model, and then we'll pass through the transformed image. And then we will do predprob equals torch dot softmax on the predlogit across the first dimension. Oh, that should be predprob, shouldn't it? And then we'll get the pred label, torch.argmax on the predprob, dim equals 1, and then we can now go predict. Maybe we call this label. No, that's all right. Predict equals, or predprob equals predprob. And then I might shorten this to round. No, that's all right. We can just leave that there. And then predict equals pred label equals pred label. Get prediction and pred prob. Prediction probability. then let's go, does the pred match the true label? And then predict equals correct, equals, does the pred label or does the class name equal, oh, we need a list of class names, because the pred label is just going to be class name. We need a pred label. Yeah, we need to convert truth we'll pass in class names here, and then we'll index on that to get the class name. Does the class name equal the pred label? Pred class and then we want to return, no, we want to append at the bottom of this list, add the dictionary to the list of preds. So test pred list dot append predict, return test pred list, and now let's try our function pred install. I'm just going to put this here. Sort data frame by correct is sort data frame by pred prob. Plot the top 5. We want descending. Plot the top 5 most wrong. I think we can do this. This is good fun. Return test pred list. Yes, do we have this? I'm not sure if this will work, but I think it will. Pred install. Test paths equals test data paths. Model equals model. Transform equals simple transform, and then class names equals class names. If this works, we should get a list of dictionaries with what we're after. Damn. Oh, we need to make sure it's on the right device. I think I need to make sure everything is on the CPU. because this is all going to be on the, make sure things in the dictionary are back on the CPU. Oh no. Hey, there we go. Now, why is this like that? This should be a list. We're breaking somewhere. Okay, so we're getting our dictionaries. Oh, we're returning a function here. Oops. Did you catch that? Maybe we want to unsqueeze the pred prob as well. Unsqueeze and get the max. Oops. There we go. Beautiful. How did we get the... We want dot item, I believe. Because we don't want it as a tensor. There we go. So we've got a path. Now we can turn this into a data frame. Import pandas as PD. So equals pd.dataframe. And then if we pass in, what do we get? Hey, there we go. Okay, now we want to sort by how do we sort by a column? Sort values, that's right. We want by equals correct, false, and then we want sort values by pred prob, and then we get a doc string here. Ascending equals true. No, we want it descending. Sort data frame by correct, then by pred prob. There we go. Oh no. We want it sorted first by I think I might be able to sort by a list. Do you get what I mean? I want to sort by correct. So I have false here, but then sort that by predprob. There we go. Pseudo Maze, what's going on, my friend? My pants are riding high. Data frame sort by one column, then another. Oh, you can pass in a list for ascending as well. Ascending, we want for correct, we want false first. So that's going to be true. False. We're just doing some PyTorch Transfer Learning stuff here. Specifically the exercises and solutions for section 6 of my upcoming PyTorch course. So we've got some exercise here to work on. And I'm doing this, number 2, getting the most wrong predictions. So the predictions that are wrong but have the highest prediction probability. And our model's actually quite good, so it doesn't have too many wrong predictions in the first place. So here's what I mean by the most wrong. So we've got 5 there. Let's just get the head of this. So there's the 5 most wrong. So it's predicted steak when it should have been sushi with a prediction probability of 0.54, which isn't actually too bad. But we've got, it's predicting sushi when it should have predicted pizza. It's predicting steak when it should have predicted sushi. Sushi when it should have predicted pizza. Steak when it should have predicted pizza. Now we want to plot these 5 images. So let's go plot the top. Let's just call this top 5 most wrong. Top 5 most wrong. Plot the top 5 most wrong images. So we want most wrong image paths equals top 5 most wrong image path most wrong image path. Is this going to give us a list? Beautiful. So for image path in we kind of don't want, let's see if we can just plot it straight from here. So for row in, let's iter rows. I know this is not really fast in pandas, but let's do that. Print row. We want our image path is going to be 1, I believe. Row equals row 1. Image path equals row 0. True label. plot the image and various details. So we need to open the image. Do we have Torch Vision? Maybe we'll open it with Torch Vision this time, just for fun. This is going to read it into a tensor. Image path. And we need matplotlib. .pyplot import plt. So that's going to get image as tensor. Let's just see what this does. plt.imshow image. We're going to need to permute that. So permute. So matplotlib in plt.title is going to be, we'll do an f string of true label is the truth. Pred is pred class. Prob equals pred prob. Let's see what happens. Oh, what do we get wrong? We need the image path as a string. Hey! There we go. Oh, look at that, friends. We have the most wrong predictions. How fun is that? Arthur asks, do I prefer Pandas or Spark? At the moment, Pandas. I've never really used Spark. You have found, Pseudomaze found a new and juicy book, Deep Transformers for Machine Learning, a deep dive. Oh. Can you send me the link for that book? I think that'd be a good book. But let's look at this, right? So this is where our model has, in other words, predicted with the highest prediction probability that it is a certain thing when it should have been something else. So for this image, it's predicting, let me zoom in. It's predicting steak, but it should have been sushi. Yeah, that makes sense. That should be sushi. But I feel like it might have predicted steak because it's got like, this could be like a pot of gravy and this could be some greens, maybe. I don't know. The truth was pizza. This predicted sushi. So yeah, they got that one wrong, but that's a kind of a messy pizza, right? This is just flat out wrong. The truth is sushi, but this predicted steak. So some room for improvement there. That's not a steak. This predicted, oh, this is a wrong label. It predicted, this is funny. This is labeled as pizza and it predicted sushi, but it should actually be hamburger. So this is just an example of where we're using our model to troubleshoot our data. This is actually a pretty cool one. So that's cool to see. And this was, it predicted steak when it should have been pizza. Yeah, this is quite clearly a pizza, but maybe the steak is because of this dark area. I don't know. But you could keep going with this and explore it. It's really fun to figure out where your model predicted wrong, but with high prediction probability. And so if we increase the data set, we could turn this function into something that could do it across a whole bunch more data. In fact, we actually have that. Like this function could work for a whole bunch more data. So I believe that might be time for the next exercise. But just keep that in mind. If you want to troubleshoot your model, show the samples where your model predicted the wrong thing, but with a high prediction probability. Predict on your own image of pizza, steak, and sushi. How does the model go? What happens if you predict on an image that isn't pizza, steak, and sushi? Oh, okay. So we need to get an image, pizza, steak, sushi, and then get an image of not pizza, steak, sushi. So let's get an image. I wonder if we can download from Unsplash an image. Let's look up pizza. So this is quite clearly a pizza, right? This is quite clearly a pizza. Let's see what happens. If I just go wget, is this going to download this image? Oh, please tell me it does. It does. Can I open that as an image? I wonder if this will open as an image. I need a way to get my own image. I've already done one on Pizza Dad, but so this is what we're trying to do. So we're trying to use our saved model to predict on our own custom image. I think this is not downloading the image, is it? Let's see if we can just dig into this and find the image link. Can we find the raw image link here? Beautiful. Wonder if we just get rid of all of that. There we go. I wonder if this will download for us. I'm winging this here, by the way. Is this going to open up as a JPEG? Let's just go download Unsplash image with Python. Okay, I thought there would be a much easier way to download an image into here. Oh, it actually did work. It's just really big. Okay. Sweet. How do we resize that image? Let's just do that. Okay, that works. I want to resize. Gigs for gigs, shocking. Trying to get an image from the internet here. Resample. Okay, there we go. We're just going to we don't actually have to do this. Let's just try it anyway. See what happens. Yeah, Pseudomaze, where's your PyTorch community? That sounds very good. I've been doing a whole bunch more PyTorch lately. Is that with Mark as well? Let's see if this works. Oh my goodness, what are we getting wrong here? There we go. Okay, we've got an image here, friends. Let's do this even more. I'm going to divide by 7. So we've got a way to get images from Unsplash now. That's pretty cool. Maybe we divide this by 10 just to make it even smaller. An order of magnitude less data. So make a function to pred and plot images. So you can still see me here? Yeah, you can. That's a Discord link. I'm not going to open it just yet on the stream, but you could, if you could DM me that on Twitter, maybe at Mr. D Burke, I'll get to that, or I'll get to it after the stream. I'm just going to create a function here. Pred and plot. We want image path. We want model, and we want to transform. So we want open image. Equals this path. So we want pred on image model.eval. We've written this code a fair few times now, but that's all right. We can practice. F string. Oh, we want the class names up here, don't we? Beautiful. And then plot.access false. Hopefully this works. I think that's all we need. Let's just see, hey? Oh, we need to... Oh, no, that should work. Pred and plot. And then model equals model. Is my face getting in the way of any of this? So what we're doing is we're just getting an image from the internet and hopefully predicting on it with the right thing. Unsplash is a great place for free images. No image found pizza JPEG. Oh, pizza.jpg. Sushi. We got it wrong. Okay, so our model gets that wrong. Classic. Wonder if we got another pizza image. Nope, that's all right. We'll just get that wrong. It's not what it's about. So let's just get an image of a truck, maybe a Cybertruck. How come there's no images of Cybertruck on here? What about Tesla? What about a burger? Nah, that's boring. What should we make a prediction on? What about a house? These are all just too... The photos are like too nice. Cool house. Yeah, see? These are all just like... They're real high quality, but they're too nice. Yeah, let's just do Apple. Good idea. Apple. There we go. Okay, so what's going to happen if we try to predict on this? Images.unsplash, that's the source. So wget that. And then let's save this to apple.jpg. And then pred and plot. What did we get wrong here? Oh, excuse me. Is this a... Oh, 6 megabyte image. We'll pred and plot. Sushi. So it gets it wrong. So our model really likes predicting sushi. Okay, so let's retrain the model for 10 epochs and what happens. So what we did there was exercise 3. So we predict on our own image of pizza, steak, and sushi. So essentially one from the internet. Or we could upload our own, you know. I'll put this in here. Here you can get an image from a website. HTTPS www.unsplash.com to try it out, or you can upload your own. So if we predict on pizza, steak, and sushi, our model is going to predict pizza, steak, or sushi. In this case, it gets it wrong. It was trying to pred on this image as sushi when it's pizza. And it predicts as this apple as also being sushi. So I think our model is a little bit biased towards predicting sushi. Unless something has happened to our class names. No. Okay, that's all right. Yeah, transformation is transformed here. It's transformed. Let's just make sure. Let's do one more so that it's not I think our model is biased towards. Let's try steak. I think our model is just biased towards sushi. See, these are all two nice photos of steak. Our model is not trained on See, that's the problem. Our model is not trained on images this nice. Yeah, the transform contains normalization. Let's try this one. This is quite clearly steak. So I'll show you the transform here. There we go. We resize to 224, 224, and we transform it to ImageNet. Let's just copy. Oh, I don't need all of that. So you can actually just delete all of this. Yeah, because we're using an efficient net trained on ImageNet, and so our model is transformed to just be ImageNet. Try again on a photo of steak. Yeah, so the model could do with some improving. Again, we're only training on 70 images per class, which is not actually that many. So we only have 70 or so pizza images. And our data isn't that high quality. So these are just from Food 101. So let's go, and then we'll change. We will get steak. Okay, there we go. Our model is not just completely sushi'd out. It actually works if you pass it in photo of that. So let's just put this one up here. Okay. So train the model from section 4 above for longer for 10 epochs. What happens to the performance? So what were we getting before? We were finishing up about 90% accuracy. Test ACK, 89. So about 90%. Let's just recopy this. We're going to have to instantiate a new model. Yeah. Let's just redo that. This time for 10 epochs. So we'll create a new loss. Create class entropy loss. And a new optimizer, Atom. $r equals 0, 0, 1. So instead of 5 epochs overall, we'll just train a model for 10 epochs now and just see what happens. We're on exercise 4 now. How long have I been streaming for? Oh, nearly an hour and a half. Let's stand up. I'll just get this model ready first. Unfreeze, or no, freeze base layers for param in model.features.parameters param.requires grad equals false, and then change the classification head. So let me just show you what we're doing here. We'll go model 1. So model 1 is comprised of EfficientNet in PyTorch is comprised of 3 main sections. We've got features. So we want to freeze all these layers. What that means is they're not going to update during training because all of these layers have been pre-trained on ImageNet. So they already have some pretty good weights. All we want to do is we want to customize. So yeah, see how there's hundreds of layers here. We want to keep average pool the same as what it is as well. We want to customize the classifier to be suited to our problem. Right now, the out features has 1,000 different classes. However, we only want 3 classes, pizza, steak, or sushi. And so this concept will go for almost any transfer learning model that you use, or any pre-trained model that you use. Generally, a model will be trained to fit a certain type of data. But for transfer learning, you want to change, you want to keep the underlying representations that a model has learned, but just tweak them to use it for your own problem. So we want to go from 1,000 out features to 3 out features. And all we want to do is we want to train this layer to suit our data. And we want to use this backbone here to keep that learned representation of what an image looks like from ImageNet and just use that to extract information out of our data. So this is what's happening. We're going through the parameters in the features layer, features section of our model, and we're turning off the gradients. So that means PyTorch will not track any of the gradients for these layers and hence will not update or change them during training. And then if we change the classification head, we can go model 1. We actually want this as model 1 too here. Model 1 dot classifier equals nn torch nn dot sequential. We're just going to keep it as the exact same as what it is, except with a different amount of out features. So classifier dropout, we'll keep that as what it is, and linear, we'll keep that. So we could even just copy this up here. So this is nn.dropout. Do we have torch nn? I don't think we have nn yet. From torch, import nn. So dropout p equals 02. We're just going to keep it the exact same, the classifier head, except for the number of out features in the linear layer. So in features is going to be 1280. That is from the features section. So if we pass an image through EfficientNet B0, it's going to turn that single image into a feature vector of size 1280. So basically it's crunching the numbers on whatever image goes through and turns it into a vector of 1280 long and goes, hey, this is the representation that I've found from this image based on what I've learned from ImageNet. Then we want to use that as the input to our final layer, but then we want to compress that feature space into the length of our class names, which is 3. So we want an output of 3, a vector of 3 as our output, and the bias equals true. That's because I've just copied this. All I've changed is this from ImageNet, which is 1,000 classes, to what we're working with. We're working with 3 classes. So then we go model 1. What do we get? There we go. So now we have out features equals 3. And then a great way to inspect our model is if we go torch summary.info. Oh no, torch info.summary. Summary, and we pass it in model 1, and then the input size is an example of how big is the so say we have an input of 32 batches, sorry, a batch size of 32 of images with 3 color channels and a height and a width of 224, 224. 224, 224 is the height and width input of EfficientNet B0. These values will differ based on what pre-trained model you use. So say if you use EfficientNet B1, you might need 240, 240. B4, I'm not sure what B4 is off the top of my head. I think it's maybe 300, 300. But you just need to put the input size in. And now torchinfo.summary should give us, or actually, I think I need to input one more thing to make sure that it tells us. Can I get a doc string, please? Oh, sometimes the doc strings in Colab work for me, sometimes they don't. Torch info. Here we go. This is what we need to do. We need to put in col names. So we want input size, output size, trainable. Yeah, that'll do. Let's see this. Oh no. Did I not get torch info? Oh, excuse me. There we go. Beautiful. So we've got all of the base layers are now not trainable, but the output layers are trainable, which is what we're after. So we've got 4 million parameters that are frozen. Oh, sorry. Well, just over 4 million parameters that are frozen, but we have just under 4,000 parameters that are trainable. So only the last layer is trainable, which is very exciting. So let's just get rid of this, so we don't have a big printout. We'll create a new loss and optimizer, and now we should be able to train our model here, except we want to train it for 10 epochs. Let's see what happens to the performance. Oh no, I'm going to stand up now too. We have our model on the wrong device. We need to send it. Okay, that's what we need to do. We need to send our model to the device. Hey, I thought I did send it to device. Maybe the classifier layer isn't on the right device. Oh, here we go. So the whole goal here of training for longer is to see if our model's performance improves from where it was previously. Okay, so the loss is going. Oh, we do get. Oh, we finish off with a lower accuracy, but a lower loss. So, Well, from this, we could plot the loss curves. Actually, let's have a look at this. We'll get the loss curves. Just copy this. I should really save this to results. Oh no, that'll work. Plot the loss curves. Oh, okay. It looks like our model's loss is continuing to go down, but the accuracy is sort of capping off here. So the loss is going in the right way, but the accuracy is not really. We could train it for 20 epochs. That doesn't really take too long. Let's see what happens for 20 epochs, hey? And I might just set the manual seed here. Okay, so it looks like the loss starts to go, oh, nope, then we go down. This is pretty good. So if we train our model for longer, it looks like we get slightly better results. So we get just over 90% accuracy. Oh, back to 80. Okay, not too bad. So right here, if we train for longer, it looks like we get slightly lower loss and potentially higher accuracy, but our model starts to look like it overfits if we train for too long. Potentially data augmentation or a learning rate decay, lowering the learning rate over time can help to prevent overfitting. So if we wanted to train for longer, that's probably what I would just introduce, is some data augmentation or a learning rate decay. So that means over time, as our model starts to train for longer, the learning rate gets smaller and smaller. And then data augmentation will, of course, introduce some diversity to our model so that hopefully the training data is a little bit hard to learn and our model learns pretty generalizable patterns. It doesn't look like overfitting too much, but it does look like if we saved our best model here, maybe 94% accuracy, 92% accuracy, if we got the model with the lowest loss, it looks like it's quite a bit lower than the 5 epochs than what we trained before, but the accuracy doesn't change too much. So that's some exploration to have a look into later on. But that was exercise 4. What happens if we train the model for longer? Let's do exercise 5. The model from section 4 above with more, let's go train. Train the model from section 4 above with more data. Say 20% of the images from Food 101 of pizza, steak, and sushi images. So I've got the data set. So right now our data set is 10% of pizza, steak, and sushi classes from Food 101. But I've made a data set of 20% of the data, which is essentially just double what we're currently using. So we can import this or download this. I've got another typo here. We can import this using the same code as we've got to get the data above, but we'll just change the link. So I'll just grab this. Or maybe we can just, do we need all of this? Yeah, we'll just adjust this to the 20%. So we'll get the 20% data. So we need to change this path. So we need the raw file path, which we can copy from here. I'm going to just save this in here. There's sushi, 20%. So that's all we're doing. We're going to append this to 20%. Let's call this image data zip path equals I wonder if that'll work. Data, we want image path plus .zip. So we're going to download this .zip from GitHub. Image data zip path. And %% data. And then we want image path. Let's check the trained 20%. So the experiment we're running here is training the same model as before, but this time with 20% of the data instead of 10%. Beautiful. So now we want to create data loaders. Oh, excuse me. So now we can use the same code as before to create our data loaders. We might as well just get this from section 6. Create data loaders. We need a transform. And we need data loaders. Boom, boom. Now, if we have a look at our train data loader, we should have called this something different to before. But previously we had 6 batches. Oh, sorry, 3 for the test data set. We're using the same test data set. Now we just have double the training data, which is great. And we can get a pre-trained model. So we're going to create another model here. Create a new model for 20% of the data. Model2 equals torch vision dot models dot efficient net b0. Pre-trained equals true. Then we'll send that. I'm just going to make this bigger now. We don't need that anymore. To device. Freeze all the base layers. For param in model2 dot parameters. Oh, we want only in the feature layers. Dot features dot parameters. Param dot requires. So we want model2 dot classifier. We might set this as a random seed because if we initialize our classifier layer, it's going to instantiate with random weights. So model2.classifier equals nn.sequential. And we want nn.dropout p equals 02. Then we want nn.linear in features equals 1280, out features equals 3, bias equals true. And we'll send that to the target device. And now we will go train a model with 20% of the data. So we'll just create a loss function. We'll just write all this out. That's okay. Loss function equals nn dot cross entropy loss. And then we want optimizer equals torch.optem atom model2.parameters lr equals 0, 1. Just the same as what we did before. But we could also just get our training code, because we've written this a fair few times over the last... Yeah, all we're going to do is grab this. So let's just train it for 5 epochs and see how it compares to model 1. Or model 0. I might also just change these to 20% so we can rerun model 0. We'll change those. So did I create, yeah, train dir 20%. So this should actually be 20%. So if I go back up here to our first exercise, let's just recreate this, retrain model 0. That way we can compare these later on. Model 0 results. We'll just run that. So this is with 10% of the data. What do we end up with? Oh. Doesn't perform very well at all. Might just restart this notebook, because before we got some outstanding results. I'll restart and run this from scratch in a second. I just want to see if this code works. Here we go, training with 20% of the data. Oh wow, we get a pretty darn good model straight away. And a very low loss. Ooh, we don't get as good a performance, but a lower loss, I believe. runtime. Let's go. I just want to see, we should end up here with model 0 results. And we want then model 0 results. We want test loss min. Then we want the same for model 2. So that's, it looks like it's performing way better, but for model 0, something's happened. So let's restart the runtime. We'll disconnect and delete. So we're going to lose all of our data here, which is okay. So now let's runtime run all. We should, hopefully, so this is model 2 is with check results with 10% of data for 5 epochs. Now we want to check results with 20% of data for 5 epochs. Try a different model from Torch Vision, not models, and see how this performs. So let's try out EfficientNet B2 on 20% of the data. How about we do that? So create a new model. Oh, but we might need to format our data in a different way this time. Create a transform to transform the data. Simple. Equals, let's go. We're going to use EfficientNet B2 for this to see if it performs better. Models, EfficientNet equals dot compose. Now this is a list. Need transforms dot resize, and then we want transforms dot to tensor, and then we want transforms dot normalize to something. So we want to use, this is for exercise 6. We're currently rerunning all of the cells to do exercise 5. Torch Vision models. So yeah, our model with %20 of the data performs pretty darn well. So if we go down here, we actually have different sizes for all of the efficient nets. B2, and we want different sizes. So B2 takes in 288, images of size 288. So that's what we need to resize our images to. What do we get here? Yes, so 20% of the data, look how much better we can get using the same model. We get a higher accuracy and we get a lower loss. So that's very good. So we get about 3 points of accuracy with double the data, and we get about half the loss with double the data, or just under half the loss. So here's where we need to resize to 288. FNet. So this is efficient net B2, and this is, let's get out of some of these extra tabs, hey? This is very exciting. We are getting very close to finishing the exercises for transfer learning. So copy that in there to tensor, and then normalize. We want this from here. Boom. Normalized. So import the data. So here's where we want to set up our data. We want to use going modular data setup. And there's a function here called create data loaders. So train data loader, FNet B2, test data loader, FNet B2, class names. So we will get equals data setup dot create data loaders. Then we'll pass in the train dirt, which is going to be, I believe we want we're only going to use, I'm going to write here, use 10% data sample for FNet B2 to compare to model 0 results. So this is a great little experiment that we're doing here as well, is we're kind of looking at the difference between using more data or using a bigger model. Yeah, so I think that's a good idea. So we're going to use the same data set as 10% for efficient net B0, but we'll see what happens if we change the model to efficient net B2. And do we get a doc string here? Transform will be our, so this is another important point, because we're using efficient net B2, that's why we have another, we have a new transform. So the transform is FNet B2 transform, which in particular changes the image size to 288, which is what efficient net B2 takes. Then I think there was one more thing that we have here. Doc string. Batch size. Well, we use a batch size of 32, of course. Import the data, create new model. So this is where we'll get efficient net B2. So model 3 is going to be torch vision. Torch vision.models.efficient net B2. We'll set this to be pre-trained equals true, and we'll send it to the target device. And then we'll get model 3. So this should be the same structure as what we've got before, but just with slightly different dimensions. So we have features, and then we have average pool, then we have a classifier with a higher dropout rate here. Okay, so let's just copy this. freeze the base layers. So for param in model3.parameters, param.requires grad equals false, and then change the classifier head to suit our problem. We want to change it. This has also been pre-trained on ImageNet. So model3.classifier, I'll set the random seed here so that we can get a kind of a reproducible system going. We don't necessarily need to set the random seed, but it's just for fun. nn.sequential. So the in features is going to be different to EfficientNet B0. Why is that? Well, that is because EfficientNet B0 it's a smaller model, so it has less features. So whereas our EfficientNet B0 had about 1,200 features here, EfficientNet B2 has 1,400. So it has about 200 more features that it's pulling out of our images. So potentially that means that it learns a better representation of our images, but that's not always for sure, right? Less might be better in the case of our example. But generally, with deep learning models, the more parameters, the better. So now let's get a summary. Model 3, let's do the input size. We have to be aware that there's a new input size as well. So 32 batch size, color channels, 288 is the image input size here. And then we want the col names. We want, what can we get here? I always forget what to call this. Torch info. Input size, output size, trainable. Let's see what happens here. Oh, there we go, friends. Look at our new model. So we have a different input shape here. So previously, if we get a summary of our model, our original model, which was 224. The input shape is 224, 224, whereas here is 288, 288. And if we go down to see the total number of parameters, EfficientNet B2 has 7.7 million, whereas EfficientNet B0 has 4 million. So now, throughout our entire model, we have almost double the number of parameters. So let's see what doubling the number of parameters does to our model results versus doubling the amount of data. So in our previous experiment, we doubled the amount of data and we saw an improvement. I wonder if doubling the amount of parameters in our model, but using the same amount of data as before, so 10%. Let me just write out our experiments. Experiments 1. Well, let's make this our own. Let's turn this into Markdown. Experiments. So we've got model 0 equals 10% data fnet b0. And then we've got model 1 equals 10% data fnet b0, 5 epochs, 10 epochs. Then we've got model 2 equals 20% data fnet b0, 5 epochs. And then we have model 3, which equals 10% data again. You see how we're changing a different lever here every time? 5 epochs. So this is double data. This is double model parameters. And this is double training time. So we saw a little bit, maybe a little bit of improvement so far with double the training time. We definitely saw a good improvement with double the data. Now let's check how we go when we double the model parameters. So we're tuning a different thing with each of these experiments. And right now our experiment code that we're writing is not very reproducible. We've kind of written the same thing a lot of times, but you could functionize this in a way that you could just run a single script and it will try these things for you in one hit. So that's something to think about. So let's continue with training this model, EfficientNet B2, with double the parameters. We need the training code. Let's get our training code. We'll just use this, the same training code we've been writing before. Another thing to keep in mind is how long it takes. So we saw a better performance with EfficientNet B0 with double the data, but it took the training time took twice as long as B0. Sorry, with 10% of the data. So which one did the best? That's what we want to find out. So right now, model 2 is performing the best. Let's see how model 3 goes. We want model 3 results. Model equals model 3. Oh, excuse me. Did we train this wrong before? Oops. Model 2. Oh no, we need to redo our results, but we'll come back to that in a sec. See what I mean? Because we're writing the same code over and over again, there's a high chance for error. So this is still 10% of the data. We have a new optimizer. We need this to be model 3. Beautiful. Okay, let's run this and see where we get to. Our model 2 at the moment is busted custard. Oh, we need all of our models to be, everything to be on the same device. Okay, EfficientNet B2 looks like it's going pretty well already. Oh, maybe 92. Oh, is that the highest we've seen so far? Finishes at 87.69. Maybe it needs to train for longer. Model 3, that is, EfficientNet B2. So let's rerun all of these. Disconnect and delete runtime. We're going to see which one performs the best. Maybe we go back up. We want to save model 1 results. We'll just check all of our training code to see if we're training the best. Model 1. Model 1 results. Model 1. Do we have model 0 results? Model 0 results. We might change this into model 0. How about that? Model 0. Model 0. And model 0. And this will be model 0. And model 0. We'll know in a second if we get any errors. So runtime, run all. Let's see. While this is all running, if we don't get any errors, let's write some comparison code down here. So model 0, we're just going to change this to all 3 of the models that we've run. Model 1, model 2, and we could plot this all out to FNet B0, this net FNet B0, for 10 epochs, and this is FNet B0 with 20% of the data. This is fnet b2 with 10% of the data. So this is double training time. If we wanted to double one thing about our model, what would it be? What do you think it'll be? Double data and double model parameters. Where are we up to training here? Oh no, we've got an error. Oops, I forgot to. Model 0 that. Import. Where we got another issue. Oh, model 0. I want to make sure this is 10 epochs. Model 1 is not defined. Model 1. I forgot to change everywhere where we need model, we need to put model 0. Ten epochs, beautiful. Oh, this is going to error, isn't it? We need model 1 results. Oh, that's pretty good. 9176. I think we should be on from here. So we're training model 2. This is on 20% of the data. So yeah, that time it took 29 seconds, something to keep in mind. Now we're training EfficientNet B2 on 10% of the data. So it looked like, in terms of accuracy, it's between EfficientNet B2 and EfficientNet B0 trained for 10 epochs. And in terms of loss, it definitely looks like more data equals lower loss. So a few experiments there, something that we could try. None really give outlandish things. It all depends, like this one was pretty easy to do, double the training time and we get lower loss and we get a higher accuracy with 20% of the data. So you'd have to collect double the amount of data. You get a little bit of boost in accuracy, but loss is also halved. So that's pretty good. And then if we use just a different model with the same amount of data as we had in the beginning, and we trained it for the same amount of epochs, we get quite a good boost in accuracy, and loss is a little bit higher. But I think if we trained EfficientNet B2 for longer, we'd probably get the best results. And potentially if we trained with more data for longer, we'd also get better results there. So a whole bunch of experiments that we could keep doing. But that has been PyTorch Transfer Learning Exercise Solutions. So I'm going to add this into GitHub right now. File into GitHub. If you're watching this in the future, you'll probably have already seen this in GitHub, but I'm going to add it to PyTorch Deep Learning. Add solution code for 06. I'm going to save this video if you're watching this live to my YouTube channel. And that way you'll be able to watch this. This is a live walkthrough of all the solutions. There are, of course, many different ways to do what we did, but this is just one way that I would do it. So I'll save it there. And then if we go to GitHub, oh, there we go. Extras, solutions. Now we have all of the code that we just walked through on GitHub there. So you could open this in Google Colab and step through it and try it out yourself. So thank you for tuning in if you're watching this live, and if you're watching this at a future date, keep learning, keep machine learning, and I'll see you next time. Peace.